Yes, I need a haircut. How's everybody doing? Hope y'all had a good break. Relatively speaking, I hope y'all are staying safe and being wise. Um, Last week, so our test is going to be next Wednesday. So I'm going to give you guys a little bit more information this week and really hit home what do you guys need to start studying for. Guys, you just got to watch TV. You just got to watch the lectures, start from the beginning of the second test lecture and just watch them. Maybe do one in the morning, one in the afternoon, but watch the lectures. That's the key thing. All right. So today what I'm going to do is talk about how Newton's three laws can be applied to rotational motion. So flashback to 310. The first lecture I gave you guys is how there's two different types of motion. There's straight line motion, up, down, left, right, front, back, 3D, and there's rotational motion, that kind of stuff, right? So the cool thing about straight line motion and rotational motion is that a lot of the time there's a combination involved, and so we call it general motion. But take this pin, for instance. Pure straight line motion of the pin would be up, down, left, right, front, back, with no rotation whatsoever. Remember, the pin can rotate three ways, just like it can move straight line three ways. Pure rotation of the pin would be where there is one fixed point or axis, and every point orbits or rotates about that axis. Now, it's hard to do that. So like even here, you saw how like I kind of drifted up and down, and so it's real hard to have pure rotation. An easier way to maybe have pure rotation would be like this, right? But even that's not pure. You see this little stem of the cap? That makes the mass off, and so there's going to be constant wobble. That's why for football, when you throw a football, there's no pure rotation. There's a constant little wobble because of the stitches. The seams throw off the mass and it wobbles. The point is that when we talk about more pure rotation motions in the body, more pure, that's why we give it R words, right? So internal, external shoulder rotation is more pure than the abduction, adduction, flexion, extension. Because look what's happening with, let's say I do abduction, okay? From here to there, here to there. Well, that's not pure. What I mean by that is the center of mass of this pin went out and up. In other words, the whole pin went up. Another way to look at abduction from here to there is it would be the same as translation, and then pure rotation. That happens all at the same time. Or we can go another way. We can say translation, pure rotation. Okay, so again, motion such as abduction, flexion, extension, those are general motion concepts that require a combination of straight line stuff and rotational stuff. So rotational stuff is important for us in biomechanics to understand, and for you guys going to therapy schools. And there's a little bit more involved in the physics than just straight line world stuff. So in straight line world stuff, we have Newton's three laws, inertia, F is equal to ma, action, reaction, force, counterforce. But with rotations, there's a little bit more to it than that. Rotation is about rotational forces or torques. Now, in mechanics, we call them torques. In biomechanics, we call them moments. Okay, so on the test, you're going to need to know what I mean when I say moment torque. Okay, so a rotational force, a force that is trying to spin something. Let's think about a force that would not try to spin something. If you had children merry around and they were begging you, my kids are like, Daddy, Daddy, please spin us on the merry-go-round. I have the potential to apply a force onto that merry-go-round to influence its motion, but I am not going to push the merry-go-round and make it move forward, back, left, right. I sure as heck ain't going to lift the merry-go-round up. So the merry-go-round, the way it's situated, is only allowed to move angularly, which is cool because it has motion, but yet it's not going anywhere. I don't have to worry about the merry-go-round leaving the spot it's in, because as it rotates, the part that's going this way gets canceled out by the stuff that's going that way, and the mass of the merry-go-round always stays still at the axis of rotation. Okay, so it's a cool way to make something move, but yet I'll not allow it to go anywhere. Pure rotation. Okay, now sometimes you want something to rotate and go somewhere. Think about the tires in your car. Now, this is all 310 first lecture kind of review stuff. But the tires are merry-go-rounds that you want to be able to go somewhere. So there's the rotation component, but then there's also the translation component. The tires are spinning, but they actually want to take you somewhere. Okay, that's general motion. So think about my application of my force to that merry-go-round. I am not going to spin that merry-go-round if I push into the axis of rotation, meaning if I push into the center of the merry-go-round, my boys are going to boo me. Come on, Dad, get serious. So if this, let's say, let me draw a picture here, and we're looking at the top of the merry-go-round, okay, and it's an oblong merry-go-round. But if I'm going to spin the merry-go-round and make my boys happy, I do not want to apply my force here. That's going to do nothing. If I apply my force here, that's me trying to shift the merry-go-round. It's me trying to make the merry-go-round go somewhere, and the merry-go-round is stuck in the ground. It's not going anywhere. So I have to be very accurate with my force. And I say very accurate, but I have to have strategy with the application of my force. I cannot apply my force parallel to the axis of rotation, meaning into the axis, with the axis. I need to apply my force. Watch, I'm going to put a big X right there. I need to apply my force perpendicular to the axis, meaning these little dotted lines are like little mythical little arms. I'm going to talk about that later, lever arms or moment arms or torque arms. But the point is that when you're parallel to this imaginary torque arm, you ain't going to be spinning you ain't even try to spin the merry-go-round. But when you're perpendicular to it, now you give that merry-go-round torque. So the point is that when dealing with moments or torques, the perpendicular distance, the torque arm or the moment arm, is more important than the force itself, because you can have all the force in the world. You can have unlimited force. If it's not applied the right way, you're not going to try to spin something. I think this ties into some layman's terms that you guys hear a lot about: technique. It's mostly technique. It's not how strong you are, it's your technique. A lot of that is inferring knowing how to apply your force to try to change or rotate things. Okay, so that's what those things mean. So let's define moment or torque for this class. So moment of torque, rotational force, rotational influence. The equation is, in layman's terms, moment or torque is equal to whatever force that's being applied that's trying to influence motion times a distance perpendicular. So the point is that in this example, the parallel example, because there was zero distance perpendicular, everything was parallel, it didn't matter that your force was 1,000,000 pounds. The rotational influence was going to be 0. Because anything times 0 is going to be 0. So again, parallel doesn't allow us to rotate anything. Perpendicular distance allows us to rotate things. And you can imagine the closer we get to 0, the harder it's going to be to rotate something. And the further away we get from 0, the easier it's going to be to rotate something. I have a couple simple little examples here. So here's a little three wing. Remember from The Princess Bride, do you have the wing? So what I'm going to do here is show you with a simple example how distance matters. Let's say I have a little compressionometer that's going to measure my push force, and I only want to apply 2 pounds of push force. Okay. So I apply, now let's define some things. Where's my axis of rotation? Here for the binder. And if I apply a force close to the axis, all it's really wanting to do is lift up the binder. If I increase my perpendicular distance, still not enough. Increase my perpendicular, whoa, there's Sir Lewis. Increase my perpendicular distance until I get far enough where my 2 pounds of force is multiplied by a big perpendicular distance, and then I get enough torque, I get enough moment to influence the rotation of the binder. Okay. So why is this important to biomechanics? Because it finishes the muscles can only pull. How do they pull? Well, they with tension, but how do they truly influence motion? With moment, with torque. Those muscles insert with perpendicular distances. Now, they also have parallel distances, and you're going to see in your book, I have an example of this. I have a ball in a socket. I'm going to get you the page in a little bit, but I have a ball in a socket, and then I have a muscle that's pulling at an angle. And what I'm trying to show you is that the parallel component of that pull is stabilizing that socket. Remember how in class I mentioned multiple times that muscles aren't just there for mobility, they're there for stability as well. So the picture you're going to see, and I'm going to pull up the exact book, a page, but here's a bone, here's a socket. And you have a muscle pulling at an angle. The muscle can't pull here because then it'd be pulling out of your skin. So it has to pull at an angle within the confines of your skin. Remember, I taught you about trigonometry. Anything that has a component, anything that's a resultant, a so what pull, has a component and a component. In this case, the force that's parallel with the bone is a stabilizing pull. It's trying to translate that bone into another bone, and that's good. And the component that's perpendicular in this case is actually the rotary component. So if you have a muscle that inserts here as compared to a muscle that inserts way out here, the further inserting muscle has a greater torque. Assume the force is the same, right? Assuming F is the same, the further away a muscle inserts, the greater the torque arm, the moment arm. So for the same force, you're going to have greater moment the further away a muscle inserts from the axis, the further away it applies its force to the axis. So this is the introduction to levers. Levers are all about torques and understanding torque arms and the advantages and the disadvantages and the trade-offs. Speaking of trade-offs, remember we talked about joints trade-offs. What you gain in stability, you lose in mobility. What I gain in mobility, I lose in stability. It's very similar. With torque arms, if you have a muscle that is applying its force very far away from the axis, there's going to be certain advantages to that come with disadvantages. And then as you work your way closer to the axis, there's going to be some advantages of that at the expense of disadvantages. So that's what Wednesday's lecture is going to be about levers and understanding that muscles that insert very far away, muscles that insert further away from joint axes have certain advantages and disadvantages. And what your body does is your body says, okay, what's our movement strategy? What's our task? What are we trying to do? And we are going to incorporate leverage, torques, moments, lever arms, muscles that give us the advantage for the movement strategy that we're trying to do. So all of this stuff comes home to play into movement strategies. What do we need and why do we need it? Another way to look at it is this. In typical mechanics, we have, things are said. I've mentioned this several times in class, like the door always moves about the wall. In biomechanics, in our bodies, man, we can flip a lot of stuff. We can get what we need. So on Wednesday, when I talk to you guys about levers, the question is going to be, well, what do we need? What kind of strategy do we need? Do we need balance? Do we need speed? Do we need large force application? Do we need the redirection of an applied force? I'm going to give you a hint on redirection of applied force. It's really cool. Imagine you bend over to grab something from the floor, right? And you come back up with it. So your movement to come back up with it. But think about what's happening with like your hamstrings, right? So let's say this is your pelvis and your body is up here and here's your hamstrings. So when you bend over to grab something, let's say you have anterior you're facing this way and your head's up here and this is your pelvis. So you're going to have hip flexion or anterior pelvic girdle rotation to help you bend over. But when you come back up, your hamstrings are going to be pulling down on your butt so that the front part can go up. You're going to change the direction of an applied force. You come up on the front because your hamstrings and gluteus maximus are pulling down on the back. That happens all the time. I pulled down on these muscles so that my head could come up. I pulled down on the left side muscles so that my right side can come up. I pulled down on one end so that the other end can go up. That's leverage. That's leverage. So changing direction of applied forces is leverage. Advantages of speed is leverage. Advantages in force application is leverage. Balance is leverage. When you're balancing on your right foot, there's certain mechanical advantages that happen there to help balance you, and there's multiple forces. There's your gravity pulling down on your center of mass, and then you have your inverters and your everters, and everybody's kind of working to kind of keep you. They have to constantly work because you're constantly swaying. Think about it like that. If you're balancing on your right foot and you're constantly swaying, that's your inverters and everters working through gravity to keep your center of mass over your base of support. It's a full-time job. They have to constantly be working to keep you balanced. Another thing we're going to do is look at how torque changes during exercises. What I mean by that is, let's assume you have a dumbbell. Okay, let's say this is a 5-pound dumbbell. And when I'm holding my arm down, gravity is passing parallel to my axis, to my bones, right? But as I raise it up, it gets less and less and less parallel and more and more and more perpendicular. Now, my arm is the same length, but the application, I'm going to put the pin down to show the application of gravity. So gravity is now farthest away perpendicular from my arm. So the torque the external moment is going to be the greatest in this position as opposed to this position. And you know that. It's harder to hold a weight out here than it is to hold it at your side, right? So we got to look at those things, and we got to understand that our muscles are going to respond accordingly. Gravity in this case changed its torque, but our muscles can't detach and insert further away if they need to change theirs. So the only way they can increase their torque is by pulling more. They have to change the F. So the dumbbell doesn't change its F. The dumbbell changes its perpendicular distance. And my muscles have no choice but just to change how much force they're applying, because they don't have that option to change their perpendicular distance. So we're going to get into those things where I'm going to teach you how to look at changing torques throughout ranges of motion of certain exercises. And if the torque goes up, your muscles have to go up. And if the torque goes down, your muscles have to go down. And there's some exercises that maintain more consistent torque. What I mean by that is machine exercises. So think about machines who change the torque as you go through a range of motion. Let me see. My son changed the picture on his thing that I had all set up, but that's okay. So think about the leg extension machine. You know, I hate that word. The knee extensor machine. Think about that one for a second. And think about how the machine is going to redirect the force. So in other words, when her knees are flexed at 90 degrees, the padding is applying its force in the X, which is still perpendicular to the axis. And when her knees are extended or are anatomical, now the padding is pushing in the Y. So the point is that the padding moves with her knee motion to consistently supply the same or similar torque. So if the torque is similar, then her muscle effort can then be similar. So that's pretty cool. Now, if she were to get out of the machine and just put some ankle cuff weights on, right? So like sometimes in therapy, you sit on the edge of a bench and you put some ankle cuff weights. So my job is to show you how when the ankle cuff weights are on and gravity is the force by itself, there's no torque when she's just dangling her legs off. And as she extends, the torque is going to get greater and greater and greater and greater. And the greatest torque is going to be here. And then the torque is going to get less and less and less and less, and the least amount of torque is there. The pin cap represents the directional force of gravity. Greater, 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 greater. Less, 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 less. Meaning that she can hold this position all day because her muscles don't need to do anything because they don't need to go against any external torque. But if she was in this position with ankle cuffs, her muscles would get tired because the torque is the greatest. So I need to get you guys to see changing torques. And so that's what we got to do this week. And remember, watch the lectures. Go back and watch the lectures. That's the best way to review. And hit me up if y'all have any questions. Later.